So Jacob was a student of mine, one of my best students of all time, I would say, and really took to CG. I was teaching a class in 3D animation, and he liked it so much he did it twice, and I let him do it. But yeah, Jacob's a great student, and now he is a grad student at UPenn. And what's the program you're in, Jacob? What's its proper name?
It's two programs, but the main one is CGGT, which is computer graphics and game design.
Nice. And so tonight he's going to be talking about kind of what he has been learning there and the kind of bridge between science and art in the field of technical direction.
Yes, hello everybody. Hello. Hello.
Hey, Jacob.
Thank you for that warm introduction. You were one of my best teachers I've ever had. So right back at you, Brad.
Thank you, Jacob.
Um, okay. So tonight's spooky presentation is the spooky science of computer graphics. If I had a cigarette right now, I would blow smoke all over the screen to make it really emphasize the point.
Spooky. Yeah.
Super spooky.
Do a quick smoke sim.
Yeah, just a quick smoke sim, just a quick one. Anyways, so tonight we're going to talk about the science of computer graphics. We're going to mix the arts and the science and kind of see what it's like to approach it with both in mind. Instead of being in one field or the other, there's something called a technical director, and they are people that kind of bridge the gap between what's under the hood and the as they call graphical user interface that the artist will use. And I want to emphasize that any questions, please ask, because I'll probably be kind of generalizing because I can't obviously go over every intricate detail of the math and everything. So if anybody has specific questions, please ask them. And let's get started. So computer graphics. Well, let me minimize this. So our tantalizing topics for the night are, we're going to start kind of with a little background on where I'm coming from. So my interests from a filmmaker to a 3D artist, and then now this kind of idea of technical director. And then we're going to get into the math and science a little bit, just talk about it generally. And then I'll talk about the program I'm in at Penn. So an introduction. So I started as a aspiring filmmaker at Ithaca College. I took the regular, live action classes. And then one semester I found this experimental class, I believe was it was called experimental at the time, and it was a computer animation, 3D animation class taught by Brad, and it sparked my interest. I took way too many classes, and that was one of them, but that was my favorite one, and I started getting really interested in the idea of mixing technology and art, because as anyone who works with CG knows, or VFX, there's a lot of tech there, and you can kind of, to varying degrees, involve yourself in the technology. Or you could try to keep it as above the iceberg as possible. It's kind of up to you. But this was my kind of first step, getting into the weeds, so to speak, of mixing kind of my interests that I'd always had in technology and art. And yeah, that's kind of where I am coming from. So let's talk about what a technical director is, because that's kind of where I'm at now. It's kind of the next step I've taken since doing straight kind of CG stuff, is I was interested in getting under the hood with those things a little bit. And a technical director will often bridge the gap between software engineers and the artists. So that can involve, I'll get into a little bit more, but building tools for the artists, making them artist friendly so they kind of know an artist perspective and kind of a software developer perspective to kind of, as I said, bridge the gap between these things. Generally, they have a background in both making art and computer programming and math skills. Examples of TD jobs could be stuff like rendering. Rendering is a very mathematical process. The idea of mapping light beams and ray tracing them, and there's a light, it bounces off something, and then what angle does it come off of that to bounce onto something else, and then how much is it scattering, how much is it remaining kind of reflective. So this the idea of rendering and like game engines and these kind of things are going to be something that a technical director will probably be involved in. That kind of goes beyond the scope a bit. An artist will use a renderer, but to build the renderer and make it kind of artist friendly, that's something a technical director might be involved in. Tools, so adding tools and plugins and add-ons to existing programs, like you're using a program and there's this thing you want to do and you do it over and over again. You add this effect and it's this combination of other effects. Well, the technical director might say, hey there, artists, you're doing all of these things over and over again. Let me make you this tool that does it in one package. And it's almost like an animation preset, let's say, if you've ever used like a preset of something, and they'll kind of turn it into this one fits all tool that can do the thing. And it's like the artist is like, oh, this process is so much easier now. I can do my art more transparently without barriers in between what I'm doing. A technical director, like I said, can kind of bridge that gap a little bit. Pipeline oversight, so creating and overseeing the general workflow on a project from maybe like even all the way from like shooting footage to getting it to the VFX artists to rendering it. They might oversee and direct this process. Simulations are something that can involve a lot of technical skills. It's something that I'm super interested in. It was kind of my gateway a little bit into some of the more techie kind of stuff, was setting up physics simulations like liquids, cloth, like destructions and all these kind of, those are all simulations. And that's something a technical director might be involved with, using maybe Houdini or their own authoring tool or something. If you ever heard about the new Avatar, they designed their own water fluid system, the Avatar life at water or whatever the hell it is. That movie, they patented a lot of fluid systems to get the water to look that way, and that's their own technology. And they had to design that. Someone's got to do those things. Problem solving, dealing with kind of issues like I said before. Maybe there's a process in the artistic workflow that's repetitive and kind of difficult. Maybe consolidating that and dealing with problems that are difficult and kind of heavy in the technical aspects. TD might do that. So yes, and as many would think, the science can be kind of spooky if you're coming from an artist perspective. Coming from a science STEM perspective, maybe it's the art that's kind of spooky, who knows. But yes, this was an alliteration, so it was easier to write science spooky. So topics, so programming and math, those are kind of the big things that a TD or somebody who wants to get under the hood with computer graphics is going to be interested in. They're going to be interested in programming, and they're going to be interested in kind of a lot of the mathematical concepts that are going on there. So as far as programming, commonly used languages in computer graphics are like Python, that's used a lot in machine learning. Java can be used in software development, and C++ is especially used in graphics. These languages are, I'm not so sure about Python, but Java and C++, they're object-oriented programming. And that means that basically, you're in object-oriented programming, you can think of a object as kind of this like you have a phone, and your phone is an object. If your phone's an object, it has both data inside of it, and it has functions that it can execute. An object is something that has data and kind of has functions. So function might be add these numbers together, and then you call this function that's part of this object, and it can do this thing like add two numbers together. I won't get into too much of the weeds, but object-oriented programming is something that's very vital to these the way that a lot of these programs work, or these languages work. And then the math. Oh, I should say that if you ever work with Houdini, Houdini is very procedural, and in that sense, it kind of replicates a lot of programming languages. That's why Houdini is an interface that's actually kind of very close. Houdini is a 3D software, by the way, for doing a lot of like simulation type stuff and also procedural stuff. It's being used for more stuff though now. But basically, if you use Houdini, that's a program that's very kind of, it gets closer to the computer level of what's going on with graphics. And it kind of replicates a lot of this kind of proceduralism that goes on in programming languages, which is something I've realized, is that the idea in Houdini of like building a tool that, like, if you want to make a rock, you make this kind of node tree that makes a rock. And then you can adjust this node tree to make different kinds of rocks. That you build like a machine that makes rocks, similar to how you, in a programming language, make a function that executes a process. So again, that's a little bit in the weeds, but it's something I've realized is when you use programs like Houdini, you're getting closer to that computer level. As far as the math is concerned, we have linear algebra as being very central to a lot of graphics stuff. Linear algebra is like dealing with a lot of matrices. I'll show some slides of that stuff. Discrete math, dealing with probabilities, statistics, and kind of that's in proofs. Some of that stuff is central to algorithms. Like if you build an algorithm, and you need to prove that it works, that you can write a proof for it. That's kind of discrete math. And then physics is something like in physics simulations and rendering, something that you're going to encounter also. So it's very interdisciplinary. This is actually a program that I wrote for my class at Penn that makes a rectangle. It's very exciting. So basically, this is the kind of thing I'm doing at Penn right now. Is this is basically an operating system subcode. So in an operating system, you have a lot of procedures that deal with input and output devices like screens and keyboards. So I built this thing that makes a rectangle, and it's as you could imagine, you could do this very easily in a program like, I don't know, After Effects. You just make a shape and there you got a rectangle. But doing it from the ground up like this is understanding that is central to being able to make something like After Effects. So, or make tools that run in After Effects is this kind of programming. This, by the way, is not any language that you're ever going to see. This is called assembly code, and it's very, 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 very computer level code. This isn't really a language that people would use usually. But this is about as like deep into the computer structure as you can go. And we're kind of starting from the ground up in my class. So this is where we're at now. We're about to get into the language C to do the same thing, actually. And these are matrices. If you've ever seen something that looks like this before, it's not quite like the scrolling green numbers of the movie The Matrix, not exactly that, but it's these arrays, these two-dimensional arrays of numbers and doing operations on them. So you have a 3D object that is defined by matrices and coordinates. So basically in a computer's memory, you have one dimension. You have rows of memory. You have like maybe in a modern computer, millions of rows of memory, maybe. And each of those rows contain information. And one row might contain the x coordinate of a vertice in a 3D program. The next row might contain the y coordinate and the z coordinate. And when you have this set up in memory in one dimension like that, but the way it's coded and the way it's displayed in a language is often in a matrix, which is two-dimensional. You can kind of think of a computer screen with its pixels. Each pixel is kind of one memory address. And then, but there's this array of pixels, and organizing them in that array in the language itself is going to make things easier for you. And if you get into GPU programming, GPUs are very good at linear algebra and doing parallel processing. So in GPU, it's going to be able to do millions of matrix calculations per second. And that's why GPUs are used to power graphics. I mean, they're called, GPUs for a reason, but they're used for the purpose of graphics because they're very good at multiplying and dividing and doing operations on 2D arrays, i.e. matrices. And so a CPU kind of brute forces it. A CPU will do one thing and then another and then another and then another. But if you think about like a screen with pixels on it, you could do all those pixels in parallel. Why do you need to do each one in series over it? It takes a long time. You got to do pixel on the far left, pixel on the far left plus one pixel on the far. You have to do it over. That's kind of how a CPU would process an image. A GPU is going to, in parallel, do all the pixels at the same time. And that's why GPUs are becoming very, very popular, even for things beyond computer graphics, because they're so good at doing these linear algebra parallel calculations. And within a pixel, there's color data, there's all kinds of things, and you can arrange them in these arrays, these matrices. Yes. And like I said, rendering. So this gets into some kind of the math and physics. You're talking about light rays hitting a surface and what angle are they bouncing off. And you're getting into some trig stuff too. And when you're building a rendering engine, you have to be able to understand these kinds of concepts. And it's a combination of all these skills that you really want to have as a technical director. This is a slide that I actually made a while ago for a presentation I made a while ago for Park Post. And it's kind of showing the math behind a composited image. So in Nuke, that's another program that, like Houdini, is kind of a little bit closer to the computer level than is something like After Effects. After Effects probably more artist friendly. And then Nuke is going to be a bit more technical, and that's kind of the industry standard for compositing stuff. After Effects and more for motion graphics kind of stuff. But in Nuke, we have the merge node. That is putting one image on top of another. And the operation for the merge node is A plus B times 1 minus A. And I have it kind of laid out here as to what those variables represent. A is the thing you're going to put on top. B is the thing on the bottom. And then A is the alpha, lowercase a is the alpha of the image. And then you kind of punch a hole into the bottom image using that alpha. So now you have on the bottom right, you have this bottom image with a hole in it. And then you put A on top of that, and you've composited two images. This is the basis of like all, well, not all, but a lot of visual effects is just putting two images on top of each other. And that's math. And in Nuke, if you know the math, it's actually very helpful. If you kind of hover over these nodes, a lot of the times they'll show what the math equation is. If you use Photoshop or After Effects, it'll be called blending modes. In Nuke, they're represented as these nodes with a lot of the same names actually. But yeah, this is a film I made, but yeah. And then we have simulations, and simulations in a lot of cases are basically using these like you could imagine a ton of tennis balls. Like these all look like little balls. And you could call those particles. And you're taking these tons of particles and you're defining the way they move. And then like if you throw a bunch of tennis balls at a wall, they might scatter all over the place. Maybe you add some viscosity, which would be, you think, add viscosity to a tennis ball. What does that mean? Well, when you have a bunch of tennis balls together, if you add viscosity, now all of a sudden they don't fly apart as much. They stick together a little bit more. And this interaction between particles on a large scale, if you mesh it, which is kind of connecting the dots, all of a sudden you have a surface. And in this case, the way these particles are moving, if you mesh those together, it kind of look like water. And that's the basis of a lot of simulations, is these particle systems. Even kind of explosions and squishy objects, a lot of the time it's going down to the level of particles. And it's turning these things into particles. And there's a lot of physics involved in that. There's a lot of physics involved in the process of determining how these particles are going to move and setting parameters for them. And that might be a job that a technical director or software engineer has. And then they set these parameters together for the artist, so the artist can slide a knob or a slider that says more viscosity, less viscosity. And what that's really doing under the hood is probably a ton of complex mathematical calculations. So let me talk a little bit about my life at Penn. So this is kind of my timeline here, is that I am starting in the MCIT program. And the MCIT program is a master's program in computer science, specifically for students who don't have experience in engineering and computer science. So it's great for me because I don't really have any experience besides some classes I finagled my way into in college. And then, so I'm starting that right now, and it's updating my background in computer science. And then I start CGGT, which is the whole reason I'm doing this in the first place, which is computer graphics and game design. And that program will teach me about merging the science that the computer science with math to make images. And we do things such as build plugins for Maya, which is a 3D program, or I think one of the projects is making our own Minecraft world. So we are basically coding a Minecraft world from the ground up. That's one of the projects we learn about. Actually, I wanted to just briefly kind of look at the description to show people what it is. Computer graphics and game technologies, master in science and engineering. Interactive entertainment, computer animated visual effects are now part of our mainstream culture, creating such CGI However, is no trivial task. It requires a blending of art and science. And that's kind of what I'm talking about. Developers spend long hours with cutting edge technology. I mean, this is a bit of an advertisement, but the underlying message is the same. And
Long hours is true though, right, Jacob?
long hours is an understatement. I would call it infinite hours, never ending hours. 3D computer modeling is one of the classes. I might waive that one because I kind of have that. Computer animation, and then you can get into these electives like machine learning, computer vision. Then we talk about physically based animation, like shaders, how do shaders work and stuff like that. And there's, like I said, there's some probability and statistics stuff, especially when you're doing machine learning and AI stuff. There's a lot of probability that goes into that. Actually, it's determining what is the most likely point in this image that is an edge, maybe, and it's detecting the edges of an image so that it can then do a automatic green screen or something. These are kind of probability things that are going on under the hood. Like I said, GPU programming and architecture. And then you see courses like Video One and cinema production. It's kind of it's a real mix of these things. He makes us take an engineering entrepreneurship class also. And then there's a thesis where you can maybe make a video game or something like that. This is actually some of my code right now for a project I'm working on, which is actually we're building a blackjack game in my Java programming class, which is exciting because I have an intimate relationship with blackjack, as some of you know. And then, okay, so getting next here is electives. Like I said, you can explore more niche interests like machine learning and these other kinds of things. And then when I graduate in a million years, I'm going to have 2 master's degrees, one in computer science and one in computer graphics. And that's going to be very exciting someday. This was a stock image of the slide, but I thought it was appropriate. A picture is worth 1,000 words. And you know, when you're programming about 1,000 words to get one image. So it really is kind of appropriate. Yeah. So why does PowerPoint want to access my camera? What does PowerPoint need a camera for? Okay, so that's it. If anyone wants to ask me any questions, I can get into more things in specifics, but I wanted to wait to see what everyone was curious about.
Thanks, Jacob.
You're welcome.
I have a question. I forgot how to raise my hand in Zoom, so can I just ask it?
No. Yes, please.
Okay, I'll wait. Okay.
No,
So you went into this program, I know because you were interested in the math and science, and you're kind of intersection of like science and art and stuff. What is are you gonna make like the next like Super Mario Brothers for like Nintendo Entertainment System? Like I know that's like a very assembly coded like video game, very simple and stuff. But like what's your end goal that you want to do for your thesis with all this?
so yeah.
It's okay if you don't know.
No, I kind of do know actually. It's a little bit too ambitious, but basically I want to make a film that exists in a 3D space that the viewer can walk around to witness the film, and they could kind of follow any character they wanted to. So it's kind of going to include game design elements and classic 3D animation elements and for film and video. And it's going to be more predetermined than a video game, but I want to do something with the idea that the viewer can kind of take any storyline that they so please within the film, and I want to set it up in such a way that there's places in the space that all represent kind of differing kind of narrative lines that one could go down. And I would like to also include AI, if possible, to kind of generatively make elements within the film so that it's always a little bit different. The idea is that when you watched it, it would always be different every time. You could never have the same exact experience. Would be cool for a murder mystery. Yes. Yes, that actually would be kind of cool. That reminds me of like Disco Elysium or something. But the way I kind of I was thinking of like a war or something. There's two sides. You can follow one side or follow the other side. But that's kind of what I want my thesis to be. Will I accomplish that within the scope of time that I have? Probably not. But that's my idea.
It's a cool idea. It sounds like a Sleep No More, if you've ever heard of that in New York City, like the interactive theater stuff where you can like follow around different storylines. Look it up. It's really cool. It sounds similar to your idea.
Cool. I'll look that up. Thank you.
You said it's called Sleep No More, Chris?
Yeah, I've gone twice, and it's awesome. It's
Nice.
like a 4-level like block of New York City that like you everyone's wearing masks and you're not allowed to touch the actors. We kind of move through this space, and different actors had different storylines, and like it's kind of loosely based off Macbeth. You're in like a haunted hotel. It's really cool.
Awesome. Very cool.
I kind of like the idea of like extremely banal elements too. Like you could literally just watch somebody like argue with their like children for like 40 minutes if you wanted to within the film.
My storyline. Yeah.
Yeah. Yeah. Literally.
Ben found out how
It's
to
not a true
read his
story.
hand.
Yeah.
Oh yes, Ben.
Yeah, there's the in the reactions, there's the lower and raise hand button. But my question was, so Jacob, you mentioned how players, I guess you could call them almost, are walking around in this space of this project you want to make. So would you be able to find a way to maybe use Unreal Engine's virtual production in that to make the environment even more convincing if you don't necessarily have a real physical space you could use? Like, for example, like AR uses real physical spaces, but you could use virtual production for places that the player can't necessarily actually go.
Yeah, for sure. The way Unreal is developing is I'm definitely going to be getting into that. That would be a great tool. When you say virtual production, do you mean like they did with the Mandalorian, like the big screens and stuff like around? Yeah, I mean, the problem with that, of course, is going to be acquiring a virtual production place to exist. Like I want it to be as easy as possible to watch. I don't necessarily only want you to be able to do it if you're in like a space like that, but that's a great idea and something I've thought about is using something like that. For sure. That and Unreal are an extremely powerful combination that I definitely want to start learning more about. So for sure.
You can project that too. So just think about using beamers, especially if you had a space where you had people moving through multiple rooms. Projectors could be an interesting option, especially if you're going to do something kind of avant-garde too. That'd be cool.
Yeah, for sure. These are great ideas. Please follow up with me if you have more.
Max?
Yeah, so you were talking earlier about how like Python is good for machine learning, and I'm just wondering like what other types of programming languages are best suited for other practices? Like
So
what would you use C++ for optimally, you know?
So this is going to be something I get more into when I'm getting into the main program, but C++ is going to be used a lot for general graphic stuff like rendering or tools for 3D modeling and stuff like that. C++ is an evolution off of the language of C, which is one of the first main languages that was developed a while ago. And C isn't used too much for mainstream stuff as far as I know. But Java is going to be used a lot for software development. Java is another huge language that people use a lot. Python is I think a lot of people use Python for a lot of scientific computing, and that's part of the reason that it's used for AI and stuff so much, because it's AI and machine learning are so math heavy. Besides that, there's another really mathy language. I can't remember the name of it, but I honestly don't know super well. I can't give you great specifics. There's also languages that are embedded into tools themselves. Like if you're using Houdini, then the language Vex is what's native to Houdini. And a lot of the stuff you're going to be doing within that program, you're going to be coding in Vex. And also in Maya, there's Mel, less language Maya uses. Nuke uses some Python stuff. Fortran, isn't that an old one?
Yeah, it was developed in the 50s. I think they still use it in some scientific applications.
Oh yeah, that one. And basically, I would say that as a general rule, a lot of the object-oriented programs are going to function similarly. So object-oriented programming is going to be a very good skill set to have, to know how that works generally. So that could be a variety of different languages that work with objects like that. So you could, if you're familiar with object-oriented programming, you can develop skills in a lot of other languages with that knowledge.
Okay, I think I have like two follow-up questions, I guess. The first would be like, so like a program like Nuke or Harmony, they like almost encourage you to build your own tools with Python or just like speed up your workflows with Python. Does that mean those programs were programmed in Python? Or can a program be like built in C++ and support Python?
Yeah, so the same way that, your computer your OS isn't necessarily made in Python, you can still run Python on your computer. So yeah, Maya's not like made with Mel, but Mel is a program developed within Maya to do things within Maya. And I don't think that Nuke is made with Python, but these programs can run the languages. I mean, someone correct me if I'm wrong, but I mean your OS that's made by Microsoft or Apple can run all these programs, but it's not made with those programs. So there's going to be a difference between operating within these tools and making the tools themselves for sure.
Cool, that makes a lot of sense. What would be non-object oriented programming?
Non-object oriented program. I mean, I'm mostly doing object oriented programming, but non-object oriented programming is going to be like the language C is not, it doesn't have objects. And what a lot of stuff with objects is like being able to do repetitive tasks so that like you're, like I said, if you're trying to do like the square root of something, you could make a math object or something that can do square roots as one of its procedures. And now you don't have to write out code for a square root every single time that you want to do a square root. You just call this procedure. In Java, it's called a method. In Python, it's called a function. In assembly language, it's called a subroutine. And you call this object, you instantiate it, and then you can do tasks using that object and its methods and data. Brad seems to know some non-object oriented programming languages. Maybe he knows better than I do.
I think they refer to them as functional programming languages. They're not object oriented. And I think C++ isn't object oriented. And then a bunch of like Fortran COBOL, BASIC, are all procedural oriented and functional programming. So if it's not using objects or the concept of objects, then it's not object oriented.
It's Java, Python, JavaScript, C#, and it says C++ are common object oriented languages. Non-object oriented language.
C is non-object, but C++
C is not, C is not an object oriented language. They didn't really have that at the time when C was developed. A lot of programs kind of build off each other. And there's this concept called abstraction in computer science where you're kind of starting with bits and bytes, and you're getting into kind of putting them together and making logic gates, and then logic gates get up to like machine language, and then machine language, assembly language, coding languages that are more high level. So a lot of these things build on each other, but sometimes you'll go back and use a program that is from 50 years ago to do something and it works just fine. So a lot of applications for a lot of different things.
But I think your point you were getting at of learning any object-oriented language like Java or Python are great ones. Will conceptually ground you in that and then allow you to more easily adopt other object-oriented languages. Just kind of like node-based workflows in one program. You learn that, you learn the paradigms, it kind of becomes intuitive in other programs.
Yeah, for sure. C++ and Java are very similar, and I'm glad that I am taking Java because that will help me with C++. Any other questions?
This might be a weird question, but like, how does one create a programming language? Like, is there like a base language for all computers? Is it just ones and zeros? Like, how does that work?
Yes, there is actually. So in a computer, you're starting off with ones and zeros. This is the fundamental way computers work. It works when a computer doesn't understand anything besides transistor on or transistor off. And then from that, you arrange those transistors into these gates so that, let's say you have a 1 and a 0, and there's this gate in between that's made of a bunch of transistors, and then the output, depending on the type of gate you have, will be 1 or 0. And then you build on top of that and on top of that, and now you have all these logic gates. I think Apple calls their thing like a logic board, that's where that comes from. And then when you have a lot of these gates, then all of a sudden you can start kind of programming in very, very basic ways. Like you can say, like, and this is what I'm doing in my class is, let's say I want to add something with another something. There's going to be a long string of ones and zeros. Maybe the first 4 bits will represent the operation code. So the first 4 bits will be 001. Maybe that means add. And then there's going to be a logic gate that decodes that and turns on the add circuit. And then the next 3 bits might be the location in memory of the first thing to add. And then there's going to be something called a decoder that sends out a message to this location in memory to write to it or read from it. The next 3 digits might be the other thing. The next 3 bits might be where you're going to store it. And that's called machine language. And then you start going into assembly language, which is when you can actually have like human language that represents machine language. Like maybe I write location R0 in memory, add R0 to R1, which is register 1, and now you're programming an assembly language. And then from that, there's something called an assembler that translates from assembly language to machine language. And then on top of that, now all of a sudden you can build these higher level languages. which is like what you see with C and C++, and then Java ultimately, and Python. And that's when you see stuff like int a equals 5, and you're declaring variables and all this kind of stuff. And all of that ultimately is getting compiled down into assembly language. And then in assembly language, it's getting assembled down into machine language. So ultimately, everything goes down to machine language. And when you're building programming languages, you're starting from, at first they were starting from assembly languages, and now you can build. It's like when you're making a hammer, like the first hammer, you didn't have a hammer to make the hammer, so you can hit it with a rock or something. Now we have hammers, and we can use those hammers to make other hammers. And that's kind of how coding has evolved. You can use programs to build other programs, et cetera, et cetera. Yeah, C++ is going to be the more you're in zone. Yeah, it's a bit closer to the computer level, so you can do things like point to memory locations.
That's what applications tend to be written into, because it's efficient. Memory uses can be efficiently controlled.
Yeah, for sure. And that's what I mean by like abstractions. You can be working at this more computer level. You can be working at a higher level program like Java, or once you could start using the program, and then you're using parameters set by the program developers and sliding sliders, and that's kind of what an artist is doing. I mean, they're coding, but they're using a graphical user interface to do it. Hopefully that's kind of answered what you were saying.
And the node tree kind of represents that perfect marriage of GUI and programming concepts.
Yeah, for sure. When we graphically represent our code, a lot of the time we'll use these flowcharts that look very much like node trees.
Exactly. Do you have you done any exercises in like pseudocode or just like logic?
Yeah, a lot of the time when we're getting our assignments for what we're going to code, he gives it to us in some kind of pseudocode, and or like yeah, I mean, a lot of the time that's more for prompts, so that he can tell us to do this without telling us exactly how to do it. But yeah, I mean, a lot of the stuff we're using is some kind of pseudocode, because at first we're not using real languages. We're using kind of this amalgamation of like we're kind of, it's a kind of a mix of like English and code to yeah.
So how long do you think you are going to track through? 2 to 3 years, you think?
It's gonna take, I mean, it's gonna take a total of 3 years, because I take it's 3 courses a semester, and there's 10 courses in CGGT, so that'll take me 2 years, and this program MCIT takes me 1 year, so it'll take me 3 years.
Okay, cool.
If anyone's interested in the program, let me know.
And have you talked to any of your professors about like research assistantships or teaching assistantships or anything like that? Do you know if that's
Yeah, I've definitely asked. They want me to get more into the program before they let me do anything like that, but I've talked to the TAs, and they're all like second year students.
Yeah.
So once I'm there for a year, I'll probably be able to, especially if I'm very emphatic about it. It seems like if I nag people enough, things will happen. So
yeah, I'd recommend it if at all possible. It really enhances the grad school experience.
yeah, the only thing that worries me is that I'm already so overloaded. Having more work on top of that is kind of frightening.
Yeah.
It's incredible how much work they give me. It is really incredible. I've never involuntarily had this much work before.
Yeah, all good things though, man. Sounds cool.
I just need to get above a C.
Fingers crossed. How are the midterms? You said were pretty brutal.
The midterms were brutal. I'm just like, I might need to talk to like like I don't know what they're called, the disability department or something, because I have like I'm like neurodivergence with stuff like time and sitting down taking tests and stuff like that. And if I don't know, I think if maybe if I could get like 20 more minutes on these tests, then I would have done fine. Like I just like I can't deal with these time constraints. I mean, you know, I took about 7 extra months to finish your assignment. Like it's that's my main problem right now is time management. So I don't know, everybody told me to talk to some office or something about extra time and give them like
Yeah.
a doctor's note or something. So
You should. When I was in calc in high school, I would always get like B pluses or A minuses on my exams, but I would be like in there for like at least 15 minutes after everybody was like gone. Like I'm still like sitting there. It's like
yeah,
different
every time.
styles, man. Different styles. But yeah, I would seek out that office and talk to people because they're accommodations for a reason, you know.
Yeah, I gotta do that.
Anyone else have any final questions?
So like this program, would they, I know you said you had some like training in computer science, but would they accept people who don't have much formal training at all? Like what was the application process like basically?
My application process was okay, so first of all, answer your question. The program is designed for people that don't have experience in computer science, like strictly do not have experience. If you have too much experience, they won't accept you. So it's really for people that come from a wide variety of backgrounds that are not computer science. So yeah, you could get in that program with no experience. I basically had no experience. I mean, in After Effects, I've set the wiggle function. You know, I've said wiggle. I mean that's my
Don't sell
computer.
yourself short.
PC particle world. Yeah.
I guess I mean I've gotten I use tools that are kind of complex, but still not really coding much. So yeah, so they my application process was finding out 2 weeks before the deadline about the program, running over to Penn, kind of begging to talk to the program director, and then talking to him and finagling my way into the program with a background that was definitely, well, part of the reason he let me in was because of the MCIT program. And also my grades weren't outstanding in the beginning of my college career. Later on, once I started doing things I wanted to be doing, they got better. But writing a compelling essay and getting some good recommendations and talking to them in person, I think helped me a lot.
Yeah, absolutely. That's great advice for any grad program.
Ben?
Ben.
Oh, Ben.
Oh, did you say so? Was the so does MCIT, does that lead directly into CGGT, or can you actually apply for CGGT separately without having to go through MCIT?
Yeah, Jackson is exactly right. The programs are separate. There's only one other person in the MCIT program that's doing CGGT next year. Most of them are like business or economics students that wanted to have a background in like data science or something like that. So you can do the MCIT all by itself. You can do a dual degree where you mix the MCIT with something. You can do CGGT all by itself. You could do dual degrees. Yeah, these programs are not inherently connected for sure.
Okay.
Well, thank you, Jacob, for all of this. We expect more updates once you can get through one semester at least.
I hope so.
And you get a breather. When does semester end, and then when does spring start?
You know, I don't even know. Sometimes
No breaks.
it feels so far away. I don't even know. I know that college students get a lot of breaks, so I assume there'll be a good amount.
Just hang in there. You'll make it.
Yeah, I hope so. It's testing my limits.
Yeah, that's good. So you know you're in the right place.
Yeah.
Yeah, Ben.
Sorry, I just wanted to say, as someone who doesn't go to Ithaca and whose major is what Jacob is working in, I thought you did a really great job explaining what we do on what anyone else is and who's in this call who's familiar with computer science. I think you did a really great job explaining it in terms of people who don't have experience with that stuff because it does get very complicated. And I even learned some stuff about the logic gates and stuff, which is something our IT doesn't really get into because they're expecting you to have um, a little bit more experience in programming. So I just wanted to say that you did a great job explaining stuff that people in the liberal arts sphere and from an art experience might not necessarily have as much experience. So I just want to make that comment.
Well, thank you very much. I really appreciate that because it's a lot of material. And what you said is interesting because like these things, like there's a common sentiment in computer science. There's this differentiation between software and what goes on under the hood with computers, and that's its own thing. I mean, there's the art, and then there's the software makes the art, and then there's under the software, there's the hardware, but it's bridging all these things into something comprehensive that kind of builds off itself. That is what I'm interested in. So I'm glad I was able to explain it in such a way. Because these things are all intimately connected. Software comes from hardware, graphics come from software. It's all connected, and that's what I'm interested in. So thank you.
Yeah, me as well. Art, I do a lot of art too, for games like 3D modeling and stuff. And RET is just starting to have a little bit more of that kind of stuff. But I really think it's what a lot of game programs should have is teaching students both because they're both extremely important. And it just makes you more of a well-rounded student if you have opportunities to learn both of those things.
Yeah, for sure, for sure. They always describe it in my program as levels of abstraction. If you have a problem and you're working in high level languages and you have a problem with a high level language, sometimes you need to get down into something lower level. Sometimes you need to get down to how the program is working itself, and you need to kind of be able to have the skills that are lower level abstractions. So that's why they start such from the bottom up with bits and bytes to C with us, because they want us to be able to look at the language and be like, oh, there's an issue with memory allocation. How does memory work? Well, I learned about memory, so I know how memory works. So yeah, it's very comprehensive.
Yeah, thank you very much.
Yeah,
Cool.
thanks for
And
coming, Ben.